Good morning, students. Next part of this topic, kinetic theory of gases. This part, pressure expression, already we have derived in the previous class. The pressure of the n molecules of the gas in a container is equals to 1/3 of nm into v mean square, this is average velocity square, by v for n molecules, or you can take it, if we talk about the particles or molecules or atoms, please. If it is monatomic gases like hydrogen, not hydrogen, helium, neon, etc., helium, neon, they are monoatomic gases, that group elements. Hydrogen, in the molecule we have the two atoms, H2, O2, N2, they are diatomic molecules. First, for derivation purpose, we imagined monatomic gases. That means only one atom is present in the molecules or particles. But diatomic mass means what? Two particles are present, two atoms are present in a molecule. Triatomic, like NH3 or CO2, three particles are present. Water vapors, we have the three atoms in a molecule. So that is a triatomic or polyatomic we can take. We are discussing now basic derivation. We are taking the derivation, imagining that it is a monatomic gas. So we got the term as 3. Okay, for others it may not be 3, other part numbers you will get 3. We got it for 3-dimensional motion along the x-axis, y-axis, z-axis of translatory motions. And this n by v, number of these, n is the number of particles, mass of each particle, this is called the average velocity, v is the volume, p is the pressure. And so in books or in some cases they mention in terms of the small n. What is small n? Is number of particles per unit volume, or number of molecules or atoms per unit volume for given volume. Unit volume is 1 cubic meter or 1 centimeter cube. Unit means 1. Number of particles per unit volume is taken as a small n. It is also called as a number density of the gas particles. Density means mass by volume. You take is number density means number by volume. And taking this p into v cross multiplication, we will get this equal to 1/3 into nm into v mean square. 2/2 you take multiplication to get the kinetic energy expression. So what you get is 2/3 into nm into v mean square by 2. This is nothing but equal to half mv square times kinetic energy you will get the gases. For n particles means total kinetic energy you will get. E is the total kinetic energy equal to n by 2, n into mv square by 2. N is number of particles. That means for each particle, if you want to take note, this for each particle's kinetic energy for one molecule, capital N becomes equal to 1 for one molecule. This is kinetic energy, each one becomes equal to half m v mean square. It is v mean square. It is called the microscopic formula for the kinetic energy of the gases. We cannot measure each particle kinetic energy, but we take it as a whole. As a whole, kinetic energy is nothing but equal to pressure into volume. Macroscopic quantity is what we can measure. What we see practically is pressure, volume we can measure, but kinetic energy each particle, gases particle we cannot measure. So, but we can measure indirectly in terms of the pressure and volumes. So, pressure and volume is nothing but equal to PV, is as the dimensions of energy. So PV becomes equal to 2/2 multiplication into kinetic energy. Kinetic energy symbol they may give you as a KE. Kinetic energy can be KE for each particles, or it may be mentioned as a E, or sometimes mentioned as a K. In your book they mentioned as a K, but K also we are using for the Boltzmann constant, so don't get confused with the two symbols. And relation for this microscopic relations formulas, we take the number of moles. Number of moles is symbol mu, sometimes taken as n, but here n is also used for other, small n is used for other symbols, so careful with the symbols, and we are using here mu. Number of moles mu equal to mass of the gas by molar mass, or molecular weight. If it is the atomic state, atomic weight you have to take. Molecular weight, atomic weight is related to the number of protons plus number of neutrons inside the nucleus of each atom. Number of moles is also equal to mass by molar mass. Total mass is nothing but equal to nm of the gas by molecular weight, which is nothing but equal to number of moles. And this mu is also equal to number of particles by Avogadro's number. Total mass is nothing but equal to of the gas is n into mass of each particle. Small m is the mass of each particle you have taken. They mentioned here. Capital M naught it is. Capital M naught is mass molecular weight of the gas. Small m is the mass of each particle. Capital N is number of molecules. Na is Avogadro's number. You already know the value. And Boltzmann constant is the ratio of the universal gas constant and Avogadro's number, R by Na. Boltzmann constant value is, you can substitute the values R and Na, you will get the expression 1.3 10 to the power of minus 23. In the problems generally they will give you the value, but you need to know units are joule per Kelvin. Gas constant units are universal gas constant is joule per mole per Kelvin. This is only joule per Kelvins. Next is if you are taking the 1 mole of the gas. When 1 mole of the gas you are taking means N equal to Na. In your textbook what they mentioned is wherever N is there, they replace with Na. But actually that is for mu equal to 1 mole. When mu equal to 1 mole, then total mass equal to molar mass it becomes, and mu is 1 means N equal to Na we have to take. Number of particles is equal to Avogadro's number for 1 mole of the gas. Next is or any materials. Here gas equations. Gas equations we have PV equal to mu RT, ideal gas equations. We have PV equal to mu RT, PV equal to NKT we can take. This is the number of particles expression, this is the number of moles expression. And the pressure, P is the pressure, V is the volume. PV equal to 2 by 3 into kinetic energy we got this. So PV also we have this equation, we can replace this relationship. Wherever P is there we can replace mu RT or also NKT. For 1 mole if you have taken, 1 mole means PV equal to RT. 1 molecule means PV equal to Kb into T. Capital T is absolute temperature. Absolute temperature means in Kelvin scale you have to take. So kinetic energy of n particles, kinetic energy of n particles is nothing but equal to, this is E is kinetic energy, means 3 by 2 into P. P, any of these expressions you can take. So kinetic energy of particles becomes equal to 3 by 2 into mu RT, or 3 by 2 into NKT it becomes. From this cross multiplication you will get the expression for E. That is the kinetic energy expression, this you have to note. So kinetic energy depends on what factors? Number of particles more, and Boltzmann constant is a constant. So temperature, more kinetic energy. Mu, number of moles, and temperature, more kinetic energy. So this kinetic energy for n particles, same thing we can express is half into m v mean square equal to 3 by 2 NKT, 3 by 2 mu RT. N for 1 particle you are taken means this only becomes equal to 1 kinetic energy, becomes equal to 3 by 2 kT, n equal to 1. And for 1 mole means this for 1 mole. For 1 mole it becomes equal to mu is 1, 3 by 2 RT it becomes. So kinetic energy of each particle is n equal to 1 if you have taken each equal to 3 by 2 kT. And kT, careful with this, they don't give B always, so they will simply give as a K. You have to be careful with that expressions and symbols. For 1 mole of gas mu equal to 1, n equal to any we can take, and kinetic energy of each is equals to 3 by 2 RT also we can take. Next is mean square velocities. Mean square velocity, what we have got is already that mean square velocity expression from this equation, equation 1. From equation 1. From equation 1, mean square velocity, cross multiply it, you will get the expression as half of cancels, this by 2 cancels, n cancels. If you are experimenting with the Boltzmann constant, then n 2 cancels, n also cancels. So V mean square becomes equal to small m, come to the right side, what you get here is 3 kT by m, 3 kT by m it becomes. And in terms of the moles, if you have taken means n equal to Na, you will get the expression, and what you get here is V mean square, 2 cancels, you will get as mu RT by Nm. Nm is nothing but equal to total mass, and replacing this in terms of n by Na, R equal to, R is equals to this terms Kb into Na relationship. If you substitute the expression to that, what you get here is, sorry, you have to replace only mu, replace mu in terms of n and m. So what you get here is nothing but equal to mu in terms of nm. You will get is mu naught, m naught. This V mean square is nothing but equal to 3 RT by m naught. This one is not actually required for us. What is required for is root mean square velocity, RMS velocity is called as. In these expressions, mu equal to 1 for 1 mole, n equal to 1 for 1 particle or 1 molecule we take. Root of mean of the square root mean square already there. For that root if you have taken, it is called as RMS velocity. RMS velocity if you take in this relation, what you get is the root, here also you get the root of 3 kT by small m is the mass of the particles, 3 RT by m naught is the molar mass. So on what factors the RMS velocity depends is, RMS velocity depends the absolute temperature and molecular weight. Depends on absolute temperature and molecular weight remaining constants, or if you take in terms of this mass of the gas, you can take particles, gas particles. What is RMS velocity? root of mean of the square of the velocities. Root of the mean of the square of the square velocity is called as a RMS velocity. This RMS velocity Vrms is also equal to under root of several particles are traveling in different direction, different velocities, then n particles are there, means we can take the square of the velocity, v1 square plus v2 square plus and so on plus vn square by n. This is equal to root mean square velocity. Root of average is mean of square of the velocities is called as a root mean square velocities. Root is for the whole thing, root of mean of the square of the velocities. But on what factors it depends is temperature. Why do we need the root mean square velocities? These gas particles travel in different directions. If you take the average velocity, for example, the gas particles while going, they don't go straight line path, they hit with each other. If you are taking the container, they hit with the container walls also. But if you are taking one forward directions, other backward directions, they hit. And if this is a V1 forward direction, V2 backward direction, so if you take the average velocity, one is negative, other one is positive velocity, opposite direction is minus velocity. So what happens is the average velocity may become equal to 0, because they have the same velocities. If you are taking average velocity, becomes 0. So we have to avoid that 0, means we have to take the root mean square velocity, because the velocity is not 0. So root mean square velocity is also called as effective velocity. RMS velocity is called as a effective velocity, resultant velocity. Very few particles might be having RMS velocity, but RMS velocity is the one which is effective value. If your wind is blowing towards you, what wind speed you are observing is nothing but RMS velocity. And sound, you are hearing the sound when the objects vibrates. Objects vibrate, produce a sound, and that sound waves are coming in the air by means of the compressions and rarefactions. In that, air particles are vibrating here and having some velocities and vibrating our eardrum. And which velocity of these air particles you need to consider, because they have the different velocities. They may have the average velocity, they may have the RMS velocity. One more velocity is called as a most probable speed velocity. Some particles have the more, so maximum number of particles have the same velocity, that is a probable speed, most probable speed of the velocities, particles. So some particles have the more velocity, some particles less velocities. We take the average and RMS, most probable speeds. Which one is effective final result you are measuring is RMS velocity. If you are finding the wind speed instruments are there, what velocity they measure is RMS velocity. So RMS value is the effective value, resultant value, what we feel is actually RMS velocity. Sound velocity in the air molecules depends on this, are related to RMS velocity, which in terms of the temperature T also. So what is RMS velocity is nothing but depends on temperature. More temperature, more RMS velocity. More mass, molecular weight is more, means velocity is less. Heavy particles of course travel slowly. So RMS velocity depends on the absolute temperature. Careful with that, means temperature in Kelvin scale. Centigrade is there, means you have to convert it into Kelvin scale by adding 273 approximately to the centigrade values. Next point in this kind of theory of gases is degrees of freedom. Number of different ways the gas molecule absorb energy. And whenever the particles are moving, for moving purposes we require some energy. That means kinetic energy of the gases depends on the temperature. Ideal gases we are discussing, please. For ideal gases, ideal gases don't have force of attraction, there is no potential energy, they have only kinetic energy. So if you take the monatomic gases are able to move along the xyz axis. That means they are free to move. They are free to move along the xyz axis. Some particle go along the x-axis, some particle along the y-axis, that axis. In between also particle can travel. We take the components velocities. So resultant velocity we take resolve into three directions. Velocity is a vector. We take it divided into three directions. X, Y, Z axis. So we say they are able to move freely in three directions along the X, Y, Z axis. Therefore, the degrees of freedom, the number of ways they can absorb the energy. They can absorb the energy to travel along the x-axis, along the y-axis, z-axis. So 3 degrees of freedom they have. So the degrees of freedom is number of different ways the molecules can absorb energy. For monoatomic gases, the gases which have only single atom in a molecule, or single atomic gases, which are like inert gases, 7th group elements, helium, neon, argon, that group elements, they are the monatomic gas examples. They have 3 degrees of freedom. What are the 3 degrees of freedom is 3 translated kinetic energies. Next, if you take the diatomic gases like hydrogen, nitrogen, oxygen, carbon monoxides, like that, the diatomic gases, particles we are mentioning, particles means small, negligible sizes, but these molecules can also travel along the xyz axis. They can travel means translational kinetic energy. They have the 3 translational kinetic energies. but they have rotational kinetic energies. Rotational kinetic energy formula what we have is half I omega square is the rotational kinetic energy formula. So rotational kinetic energy is half I omega square. I is the moment of inertia here. I is moment of inertia. Moment of inertia of rotating objects. More moment of inertia, more difficult to rotate the object. Once rotated, difficult to stop also. But for the particles have the very small size. See, the particles axis is passing through this axis is passing through the particles. If you want to spin them, the moment of inertia is negligible. Along this y-axis, if it is rotating about the y-axis, then this Iy equal to 0 we have to take. Even if the spinning is there, the moment of inertia is 0 because the radius of the particles. Word particles, big spheres means moment of inertia is not 0 if the axis is through the diameter. But for small particles, moment of inertia is 0, the kinetic energy is 0 when the axis is taken along the y-axis. But if the particles are like this rotated here and here, this axis, that is a bond line connecting the two atoms, we cannot, if you spin like this, one atom is here, other atom is here. If you spin like this, moment of inertia is 0, it is not absorbing any energy. It does absorb, but negligible energy. We don't consider that energy. So that energy is not is 0 when for this rotation along the axis passing through the particles. But we are dividing the this axis into 3 parts: x, y, z axis. If it is rotating along the y-axis, particles are located along the y-axis, Iy is 0. If the particles are located along the x-axis, Ix is 0. If the particles are along the z-axis, Iz is 0. So in this diagram I mentioned along the y-axis, therefore Iy is 0 you will get. So but it can rotate like this. About the x-axis it can rotate, along the z-axis also it can rotate. About this x-axis it can rotate, they will get as Ix, moment of inertia is Ix. About the z-axis it can rotate, that means particle like this rotation would consider, it can rotate like this or it can rotate like this. Along the Iy 0 but Iz, this is Ix, this is going to be Iz. Along the z-axis, along the x-axis not 0. So what is the moment of inertia along the x-axis? The moment of inertia x-axis Ix. So kinetic energy is half I omega square, means k kinetic energy. This is related to the rotational kinetic energy along rotation about the x-axis, Ix omega square. And kinetic energy along the z-axis is equals to half Iz omega square. So total kinetic energy of rotation is nothing but equal to kinetic energy half, in this diagram related, Ix omega square plus half y is 0 plus half Iz omega z square. This is a total rotational kinetic energy. But how many degrees of freedom that can have is to rotate along the y-axis, it's not absorbing energy. To rotate along the x-axis, about the x-axis absorb the energy. About the z-axis absorb the energy. That means it can absorb the energy to get the kinetic energy 2 types. So 2 degrees of freedom you will get for diatomic gases, 3 rotational kinetic energy and 3 translational kinetic energy, 2 rotational kinetic energy. Total is 5 degrees of freedom. This number you have to remember. This is for ideal gases. What I discussed is ideal gases. Whether this is ideal or not, for monatomic gases no problem. For diatomic gas you have to be careful. This is for ideal gas. But if you are taking the real gases, at high temperatures for the real gas, if you have taken, apart from the real gases have the force of attraction of the molecules. Due to the force of attraction, you will get the potential energy also into consideration. So if you are taking this potential energy also into consideration, their particles will be vibrating to and fro. Apart from this rotational, 3 translational, 2 rotational, and we have the vibrational kinetic energy. But vibrational energy is of 2 parts. One is because the vibrational kinetic energy moving to and fro like this about the y-axis, if I taken, the particles will vibrating to and fro like this. Like a spring, you can imagine a spring connected with the 2 particles oscillate like this. The small displacement is y if you have taken, or delta y if you have taken, then the velocity is equal to dy by dt. Half m into dy by dt is related to vibrational kinetic energy. M is the mass of the particles. Whereas the potential energy, this is a combined mass we have to take actually, and whereas the potential energy also between the potential energy also changes due to the attraction. The potential energy is nothing but equal to negative value attraction indicates, but we are taking here magnitude to get the total energy half ky square. This k I am taking as a k prime. This is not a Boltzmann constant, it is a proportionality constant value. It's called as a force constant. But they don't ask you the details, you just know how many degrees of freedom it is having. For diatomic molecules, it is having, the ideal gases have only 3 translational, 2 rotational. Total is 5 degrees of freedom. Monatomic gases has 3 degrees of freedom. And For real gases, you can take additional vibration is also there, means that will turn out to be 3 plus 2 plus 2, 4 plus 3 is a 7 degrees of freedom we can get. Most probably they don't ask related to this vibration kinetic energies, they will be asked only related to the ideal gases. Next is vibration kinetic energy, just now I explained, is nothing but equal vibration is half mv square, velocity square is dy by dt differentiation, potential energy is k proportional to constant k into y square by 2. Total energy is sum of these two energies. So 2 degrees of freedom we take. If you take the triatomic gases, 3 particles are there in the molecules. Then axis we can take along the x-axis, y-axis, this is the center of mass, this is going to be x-axis, z-axis. About the center of mass of the particles, the molecule can rotate along the x-axis, y-axis, z-axis also. That means we have 3 translational, 3 rotational along the x, y, z axis. The rotational is translational kinetic energy is along kinetic energy along the x-axis, kinetic energy along the y-axis, kinetic energy z-axis. And rotational kinetic energy is also 3 axes we can take. Kinetic energy rotational along the x-axis, that is half Ix omega square, omega nearly equal in all directions, so omega square only we can take instead of omega square also, plus half Iy omega square, omega is equal, omega x, omega y, omega z nearly equivalent, half Iz omega z square. So 3 degrees, 3 plus 3 total is 6 degrees of freedom for the triatomic gases. So you can have more than triatomic gases, no, f degrees of freedom you have to take the expressions.